Hi, I'm Chetan Bornarkar and I'm presenting register renaming in a pipeline processor. Consider I've written the program using high-level language. When I compile the code, the compiler will translate the code to symbolic registers and then to registers available in the microprocessor's instruction set architecture. But with the limited amount of registers available in the processor, the compiler will reuse the registers while translating the code. Now this register reusing creates hazards, data hazards like name dependency and a true dependency. Let's see an example which shows name dependency and true dependency. In this program, register R1 is being reused. Now this results in a true dependency between the first instruction and the second instruction. Moreover, it will also result in a name dependency between the first instruction and the third instruction. From a programmer's perspective, we assume that the code will be executed in a serial fashion. That is, multiplication will be executed first, followed by the first add and then the second add. Now assume that the mul instruction requires 4 clock cycles while the add instruction requires 2 clock cycles. So to execute the entire program, we will require 8 clock cycles. Now this is an inefficient approach. To improve the efficiency, we use or rather opt for an out of order execution. This allows us to execute independent instructions while other instructions are still being executed. In this case, if we look at the add R1, R5, R6 instruction, it is a completely independent instruction from the other two instructions. And we can execute this instruction while the other two instructions are currently being executed. This approach improves our efficiency as well as our throughput. But there is a problem. The add R1, R5, R6 uses a destination register R1, which is also used as a source register in the previous instruction. Since add1 R5 R6 instruction is pulled so early and is executed that the second instruction's R1 value is updated. Now this updation of R1 is wrong because it is an out of order updation, and this will result in a wrong value being put in the register R4 and will change the flow of execution. So how do we avoid this name dependency and still have an out of order execution? We use register renaming. In the register renaming, we change the name of register R1 to R7 in the third instruction. Now this makes our third instruction completely independent, and even if it is executed early before the two instructions are executed, it will not affect the code execution flow. So how do we achieve the register renaming? We use a RAT table, that is a register aliasing table. This register aliasing table is mapped with the ARF using an external control logic, where ARF stands for architectural register file. The RAT table has a valid, a tag, and a value fields in it. Henceforth, when we access a register, we access the RAT table and not the ARF directly. Let us explain how the register renaming works through a program. Consider the previous program. When the multiplication instruction is in the fetch cycle, the RAT table is filled with valid and initial data. Now since the data is valid, all the valid bits are set to 1. When the multiplication instruction is in the decode cycle, the source register R2 and R3 are loaded from the RAT table and placed in the execution table of the multiplier. Now if you notice that since the data are valid in the RAT table, the ready bit is set to 1. And since the ready bit is set to 1, the multiplier will proceed with the execution stage. The multiplier will place the result of the instruction back in the location of address by U, and it will also store the result in the register R1. Since it takes 6 clock cycles to execute the instruction, we store the tag address of U in the RAT table, and since the value is not being computed, we reset the valid bit. In this scenario, whenever the next time another instruction addresses R1, we place a tag value and ignore the value field in the rat table. In the next clock cycle, when the second add instruction is in the decode stage, we load the source registers R1 and R3 from the rat table. Now R3 is valid in the rat table, and thus the ready bit is set in the execution table of the adder. But since the R1 result is still not computed from the previous instruction, that is a mul, its tag value is set, or rather loaded in the adder's execution table, and the ready bit is resetted. The ready bit is resetted because the value is not available yet. Now since the value is not available yet, the adder will not proceed with execution. Now this is a scenario of a true dependency, because the R1 register is still dependent on the execution of the previous instruction. In the next clock cycle, the second add instruction, that is add R1, R5, R6, is in the decode stage. Now the source is R5 and R6, which is present in the rat table and is valid, is loaded in the adder execution table. Now since the value are valid, the ready bit is set to 1 and it can proceed with the execution. Now the result of the adder will be stored in the location B of the adder execution table, as well as the value would be stored in the register R1. Now since the value would be stored in register R1, the tag address of register R1 in the rat table is updated to value B, and still its valid bit is reset since the result is not available. After 2 clock cycles, the multiplier as well as the adder will be in the commit stage. Now in this diagram we have assumed that there is a single data bus, and to avoid the conflict amongst the result of the two adder and the multiplier, we assume there is a selection logic which will choose the result of multiplier first and then it will choose the result of the adder next. The result of the adder or the multiplier is in a format that is it has a tag followed by the result. In this case, the multiplier will have a tag of u and the result of 6, that is 3 into 2 is 6. Now this value is broadcasted in on the data bus in the entire machine memory. Now wherever the tag value matches, its respective value has been updated. In this case, it will be updated in the A location of the adder execution table. And since the value has been updated, its ready bit is set to 1 and this instruction is ready for execution. Similarly, the output of the adder, that is B and 11, that is the location B, and the output of 5 and 6, that is 11, is loaded on the data bus and it will be updated in the register R1. Now since the value is updated, its valid bit is also set. Now if you notice, we have executed the two instructions without affecting the code execution flow while improving the code efficiency. Thus, when the second instruction add executes, or rather is in the commit stage, it will have been executed in the correct flow which a programmer expects. Thus, we have avoided name dependency using register renaming. Finally, when we update the value in the rat table and set the valid bit, this value will then be written in the ARF, that is actual registers. After the valid bit is set, the value from the rat table is then updated in the architectural register file, that is actual registers used by the processor. So to conclude, register renaming is used to avoid name dependency when using out of order execution in a pipeline processor. This improves our throughput and our efficiency. Thank you.